Hello and welcome to today's session. This session focuses on learning outcome 2 LO2. Understand algorithmic complexity and appreciate its importance. In this video, we will explore what makes an algorithm efficient as data grows. You will learn about the core principles of algorithmic complexity, including time and space considerations, and understand how these factors impact performance and scalability in real-world applications. Algorithmic complexity measures how resources like time and memory grow with input size. It focuses on time complexity and space complexity. This analysis is independent of hardware or programming language. Understanding these aspects helps predict performance and make informed design choices. Ultimately, it ensures systems can handle larger datasets effectively. Time complexity examines how an algorithm's running time increases with input size. It highlights dominant operations and ignores minor factors. Linear algorithms grow proportionally with input, while others may grow logarithmically or quadratically. Recognizing time complexity prevents choosing inefficient solutions for large datasets. It is crucial for developing scalable systems. Space complexity assesses how much memory an algorithm needs as input size grows. It includes memory for input data and additional structures. Faster algorithms might use more memory, while slower ones use less. Understanding space complexity aids in prioritizing performance or memory efficiency. This is vital in constrained environments. Algorithmic complexity is closely tied to data structures. The same algorithm performs differently based on data storage. Searching in arrays, trees, or hash tables varies in complexity. Understanding this relationship helps match algorithms with efficient data structures. It ensures optimal performance and resource usage. Complexity matters due to growing datasets in real-world systems. Poor choices lead to slow responses and high costs. Key reasons include scalability, efficiency, and predictability. It encourages selecting suitable algorithms and structures early. Complexity analysis supports maintainability and system reliability. Correct. Big O notation describes an algorithm's upper bound complexity. It shows worst-case resource usage as input grows. Common examples include ON for loops and O log n for binary search. Big O provides a clear performance estimate. It is essential for designing scalable systems. Little o notation indicates strict upper bounds. It shows that an algorithm grows slower than a compared function. Linear time algorithms are ON squared as they grow slower than quadratic. It is less common but valuable for theoretical analysis. It precisely compares algorithm growth rates. A single for loop through n elements has O complexity. Nested loops result in ON squared due to multiplied operations. Such loops can cause performance issues with large data. Understanding loop impact aids in efficient design. It helps avoid unnecessary computational costs. Recursive algorithms make multiple calls affecting time and space. A function reducing problem size by 1 has ON complexity. Splitting problems like merge sort results in ON log n. Recursion increases space due to call stacks. It requires careful management to avoid overflow. Space complexity considers additional memory beyond input. In-place sorting uses O(1) extra space. Auxiliary arrays of size n use ON space. Recursive algorithms often use own space in the worst case. Balancing time and space is key in design. Design considers loop impact, recursion necessity, and memory use. Algorithms must scale with data size. Big O and little o notation justify design decisions. They ensure clarity and consistency. This approach supports effective and scalable solutions. P and no problem classify problems based on solution efficiency. P problems are solvable in polynomial time. No problem problems have solutions verifiable in polynomial time. The P equals no problem question remains unresolved. It impacts cryptography and optimization understanding. Linear search checks each element with ON complexity. Binary search halves a sorted list, achieving O log n. Sorting adds initial cost but reduces search time. This demonstrates how constraints can improve efficiency. Design choices affect performance outcomes significantly. Array insertions may require shifting, leading to ON complexity. Linked lists allow O(1) insertions with known positions. Finding positions in linked lists requires ON traversal. The choice depends on data usage patterns. Fast access versus fast modification is a key trade-off. Recursive algorithms are often clearer but can increase complexity. Fibonacci sequence recursion has O(2) complexity without optimization. Iterative or memoized versions reduce it to ON. Elegance does not guarantee efficiency. Design must consider computational costs. Bubble sort has ON² complexity, performing poorly on large datasets. Merge sort scales better with ON log n complexity. Quick sort averages ON log n, but can degrade to ON². Choosing the right sorting algorithm impacts performance. Time complexity is crucial for large data handling. Improving time performance often increases memory usage. Memoization increases space complexity but reduces time complexity. Dynamic programming frequently uses this approach. Balancing time and space is vital based on system constraints. Design involves choosing acceptable trade-offs. Faster computing improves practicality, but not problem class. Quantum computing speeds up some problems, but not all. It disrupts cryptography, pushing toward post-quantum solutions. AI aids optimization, but does not change complexity classes. Future technologies expand tractable inputs, but do not solve no-problem complete problems. Open problems like P versus no problem define efficiency limits. They guide algorithm design strategies. Approximation and heuristics are often necessary. Future tech expands input ranges but does not simplify no-problem hard problems. Classification directs where to aim for efficient solutions. Conclusion. The video highlights the importance of leveraging complexity to develop efficient and scalable solutions. By mastering these techniques, one can achieve optimal outcomes and drive innovation in problem-solving. Feel free to reach out on WhatsApp at 07484361688 if you have questions. Our team will be delighted to help. Thank you, and see you at the next session.